Hey student, one more topic from the wave motion, that is open organ pipe. Please do like and subscribe Nature of Physics. I am your Kiran Kumar. See, open organ pipe is a cylindrical tube with the air column. So both ends are open is called open organ pipe. And at open ends always antinodes form. See student, everywhere in 3 diagrams antinodes only form. And next, always longitudinal stationary waves form in the open organ pipe or closed organ pipe. Also, any organ pipe there is a longitudinal stationary waves, but in stretched string transfer stationary waves will be formed, student. But remember, only in the pipes longitudinal stationary waves will be formed. Okay student, so that open organ pipe, see first diagram, second diagram and third diagram represented, taken a tuning fork and vibrated with a rubber hammer kept at any open end of the pipe, so that here the longitudinal stationary waves will be formed. Clearly, step by step I am going to explain. See, the length of the pipe is remains same in the 3 diagram. So first diagram and also second diagram and third diagram, length of the pipe is remains same, but we will get the different wavelengths based on the derivation I am going to write. In this open organ pipe or closed organ pipe, particularly we are discussing about the open organ pipe, harmonics and overtones will be takes place, student. So what is the fundamental frequency? The minimum frequency with which stationary waves form is called fundamental frequency. Then harmonics and overtones are representing alternate name of the frequency, student. So that harmonics, the frequencies which are integral multiply the fundamental frequency is called harmonics. And next overtones, the frequencies higher than the harmonics is called overtones. Harmonics and overtones all are representing the frequencies only. Okay student, step by step with diagram explanation we will discuss about the harmonics and overtones, about the diagram and derivation, both are related to each other, student. Okay, see I am going to explain both ends, open ends, that is antinode, and between them at least one node clearly represented. This is the forward wave and this is the reflected wave. Okay, so half of the loop represent the lambda divided by 4, remaining half of the loop represent the lambda divided by 4. For first one I am considering wavelength is lambda 1, student. Okay, and second one representing lambda 2, third one is lambda 3. Frequency is open pipe is open, that's why n not representing frequency here, and second one n1 and next one n2 representing continuation we will discuss. See, first derivation, the fundamental frequency or first harmonic of a open pipe will have 2 antinodes at both open ends and at least one node will be formed between them, student. Notice that 2 antinodes at open ends, between them at least one node will be formed. Okay student, so that the distance between the node and antinode is divided by 4, student. Okay, so the derivation is writing, one is length of the pipe, second one is wavelength and third one is frequency. The length of the pipe is representing how much is there, student? Lambda 1 divided by 4. So writing here lambda 1 divided by 4 plus remaining length is lambda 1 divided by 4. So that L which is equal to 2 lambda 1 divided by 4. So I am getting here L which is equal to lambda 1 divided by 2. Okay, so now wavelength lambda writing, student, here wavelength lambda which is equal to lambda 1 is equal cross multiplication, how much we will get, student? Lambda 1 which is equal to 2L. Okay student, cross multiplication I did from the length, so I got the wavelength lambda 1 which is equal to 2L. Next frequency I am going to write the frequency basic formula. N is equal to V divided by lambda, student. Here lambda is written as lambda 1. Okay, and V is the velocity of sound, that value is 333 meter per second approximately. so that V represent velocity of sound, that value is remains constant approximately, that is 330 or 333 meter per second. So basic formula, frequency is equal to velocity divided by wavelength. In this, wavelength is replacing from the above equation, so that this is a open pipe, so that representing N naught, which is equal to V divided by lambda 1 is I got 2L. So this is representing equation number 1. This is the fundamental frequency. What is that, student? Fundamental frequency or first harmonic of the open pipe. What is the fundamental frequency? The minimum frequency with which stationary waves form is called fundamental frequency. Okay, student. So this is representing, what is that? First harmonic or fundamental frequency of open pipe. See, student. And next I am going to explain for the second harmonic or first overtone. Proof also I will give to you, just wait. Okay, of a open pipe will have 3 antinodes. Okay, one antinode increase, open ends 2 antinodes, and between them 1 antinode form, comparing to the first diagram to second diagram. So there 3 antinodes and 2 nodes, student, 1 and 2. Okay, so node and antinodes here, how much? 3 antinodes and 2 nodes, student. What is the node? Node is the zero displacement from the mean position. What is antinode, student? Maximum displacement of the particle from the mean position. See there, maximum displacement of the wave. Node area displacement is equal to 0. Okay, student. So now the length of the open pipe in the second condition, okay, 3 antinodes are there, 2 nodes are there, that is second harmonic or first overtone representation. Length of the pipe, length is remains same, L, which is equal to lambda 2 divided by 4 plus lambda 2 divided by 2 plus lambda 2 divided by 4, writing, student. Okay, so length L, which is equal to 2 multiplied and 2 divided there, so I will get 4 lambda 2 divided by 4, student. So 4 is get cancel. I am going to get the length L, which is equal to lambda 2, student. Okay, and then continuation derivation here, wavelength lambda 2, which is equal to L. Okay, so clearly represented, L is equal to lambda 2 is equal to L, student. Okay, so replacing in the frequency equation N1, which is equal to V divided by lambda 2, writing here. See, student, N1 represent the first overtone. Okay, now lambda 2, already we got lambda 2 is equal to L, is replacing here. That's why N1, which is equal to V divided by lambda 2 is L, student. There is a relation between the fundamental frequency and the second harmonic. For this I am going to do like this, 2 multiplying and 2 dividing, N1, which is equal to 2V divided by 2L, student. So we know very well fundamental frequency N0, which is equal to V divided by 2L, is replacing here. I am getting N1, which is equal to 2N0. This is writing as equation number 2. This is representing 2. 2 represent the second harmonic and 1 represent the first overtone of a open organ pipe, student. And then third derivation, continuation. See, student, for third derivation, step by step we will discuss about it. So third diagram here only. Yes, student, that is third harmonic or second overtone of a open pipe. That proof we will discuss in the derivation. Okay, we'll have the 4 antinodes and between them 3 nodes. See, first diagram is 2 antinodes, both ends, between them 1 node, and second diagram we have 3 antinodes, and third diagram we have 4 antinode. Antinode is 1 by 1 increasing 1, even though node also increasing. First diagram 1, second diagram okay, 2 times the n, and next third one 3 n's are there, 3 nodes are there. See student, for this length of the pipe is L, so length of the pipe with respect to wavelength is writing, that is L, which is equal to lambda 3 wavelength considering divided by 4, distance between node and antinode is lambda by 4, plus next one is lambda 3 divided by 2, next lambda 3 divided by 2, distance between node and node is lambda by 2, plus this is lambda 3 divided by 4 between node and antinode. So here I am going to get L, which is equal to, here 2 multiplied and divided, here also 2 multiplied and divided, 2 plus 2 4, plus 1 plus 1, that is 6 lambda 3 divided by 4. Okay, so finally I am getting here length of the pipe, that is L, which is equal to 3 lambda 3 divided by 2 student. Okay, this is the length I got. After that I am writing the wavelength equation. So wavelength lambda 3, which is equal to cross multiplication 2L divided by 3 student. So first I got the length, after that based on this I got the wavelength, and next I am going to find the frequency, that is N3, which is N2, which is equal to V divided by lambda 3 student. Basic formula wavelength. Okay, lambda 3 is considering for the third diagram. Okay student, see clearly represented lambda 3. N2 is the second overtone student. V is the velocity of sound, and lambda 3 is replacing from above equation, so that N2, which is equal to V divided by 2L by 3. Okay, rearranging that equation, that is N2, which is equal to 3 into V divided by 2L. Okay, but we know very well the fundamental frequency of the open pipe, so that N also we can represent frequency. Okay, that is N naught, which is equal to V divided by 2L student. Okay, so replacing the value in the above equation, that is N2, which is equal to 3 N naught. This is I can write as equation number 3 student. Equation 3 representing here third harmonic or second overtone of open pipe. Okay student, and I am going to write the ratio. The ratio of the frequencies in the open pipe is open pipe, that is mu frequency written there, mu naught is to mu 1 is to mu 2, which is equal to, we got the derivation, the value is N naught is, tell me student, that is second one 2 N naught is, and third one is equal to 3 N naught. N naught is cancel, so that frequency mu naught is mu 1 is mu 2, which is equal to N naught is N1 is N2, which is equal to 1 is 2 is